my eyeballs. Okay, so well, today we're starting discussion of group actions. So there's a little bit about this already in the weekly handout, but let me just sort of restate what's there. So what is a group action? So a left action of G on a set X, so G is a group on a set X, is a map. This is a homomorphism from G to the automorphisms just as a set of X. So in this group of automorphisms of the set X, and that's just all bijective maps from X to X. And sort of the multiplication is composition. So Fg of X is equal to F of G of X. Okay. And by the way, there's sort of, and I should highlight this as a choice. Some people write composition the other way. So like some people would write sort of F composed of G sort of of X as sort of G of F of X, depending on how you, probably depending like actually geographically where you grew up, that might change. But anyway, this is my convention. And that's sort of related to the fact that this is a left action and not a right action. So equivalently, you can sort of for every element X and G, you get a new element. And so every element X of your set and G of your group, you get a new element G dot X of your set. So that's G acting on X, such that so G of H dot X. So if I multiply G times H and I do it X, this is G dot H dot X, and E dot X is equal to X. So this is just rephrasing that it's a homomorphism. Okay, so you also have a right action. So if I just say action, I always mean a left action, but sometimes it's actually convenient to have both available. So even today, there'll be at least one time where we'll want to use a right action instead. Okay, so a right action is, well, you can think of it as a map from G op to opt set. So G op is sort of same group. So same underlying set. But sort of a new multiplication. So G. So G up is sort of what you get by sort of reversing the order of multiplication on your group. A note sort of G is isomorphic to G op via so G goes to G inverse. So some conventions of right versus left are innocent, and this is sort of left and right actions are sort of innocent conventions because since G is isomorphic to sort of its opposite group, you can always turn a left action into a right action. Sort of. So if G acts on X, so this is the notation for left action, then sort of X dot G. Yeah, so right actions you write as multiplication on the right, and well, you write as sort of X dot G, so you write sort of G acting, but on the right on elements, and then sort of the composition law sort of looks like this, except sort of organized in the right way. So, but you can sort of, if you start with a left action, you can sort of get a right action out of it by just doing X dot G is equal to G inverse of X. So that's another way to say sort of a right action is sort of the same as a map from the opposite group to automorphisms of your set, but G is isomorphic to G-op from this, and sort of vice versa. Okay, so I mean, this is something that's sort of often wiped under the rug, but it's actually pretty important. Usually what happens in the end for group actions is sort of you basically always use left actions, but sometimes what you're sort of given naturally is a right action, and you always convert it into a left action by sort of composing with the inverse. So like a common way this happens, yeah, well, and the reason this sort of is a convention that needs sort of some fixing is because there are certain natural operations that sort of reverse the order of actions. So for example, if you have a group acting on like a topological space, and then you look at the continuous functions on the topological space, sort of a right action on the topological space sort of naturally gets turned into a left action on sort of continuous functions, if you sort of think about it. So then you sort of also need to use an inverse if you want to like preserve a right action or sort of, well, anyway, it's, yeah, so this is neither here nor there, but just to sort of point out sort of this left versus right business, like it is something you need to be aware of because it does come up. Like there are like times when you need to sort of distinguish, but like in the end, you can sort of always turn everything into a left action or turn everything into a right action. Sort of there's a canonical way to do it. So once you sort out all your signs and sort out all your conventions, like nothing you do will ever depend on this choice. But somehow, somehow you should be aware that like there are these two different things, and sort of they sort of both happen, and at some point you need to sort of sort out everything to arrange things. That won't happen much in our life though. Okay, so good. So hopefully you've all seen some group actions before. Otherwise, that wasn't a very good introduction to group actions. But I think probably most of you encountered this in your undergraduate classes. And I guess we'll find out, because why don't you give me some examples of group actions? So someone wrote, we have the fundamental group of a space acting on the set of sort of covering maps, say it this way, acting on well, I'm not sure what the notation meant, but sort of, this acts on sort of any covering space. Acts on okay, good. Sorry, your finger's not writing. So Sn acts on the set 1 through n, right? So in Sn, in fact, is equal to the automorphisms of 1 through n. Good. So what are some more examples? Okay, well, I'll throw you guys a bone and I'll do one. So for example, if we fix a vector v, let me be super concrete. So let's look at the vector. So 1, 1, 0. Well, I'll do 1, 1, 1. So, okay, then I get an action of the real numbers with addition. So the real numbers of addition is a group on the set R3 just by sending sort of v dot t dot x is just tv plus x. So this is an action of by translation. So this sort of just is a group of real numbers acts on sort of R3 just by translating sort of everything like in this sort of, I don't know, if in my frame of reference, it's sort of translating into the top right corner of my monitor. I guess that's true for you guys as well. So that's a group action. So what are some other group actions? Yeah, good. So G acts on G itself. So G is a group, acts on G as a set. Just by sort of G dot H is just G times H. This is the left multiplication action. This is a left action. You also have sort of G acting on itself by a right multiplication. So this is H dot G is equal to HG. So now this is a set. This is a group. And you can turn that left action into, so this is the right multiplication action. You can turn that sort of right multiplication action into a left action by doing the inverse. So you do G dot H is equal to H times G inverse. So this is the right multiplication action sort of viewed as a left action. You get this one. Okay, good. What else? Yeah, great. So if X is a topological space, well, then homeo X acts on X. So it's the homeomorphisms from X to itself. And indeed, in the homeo of X, that's definitely, like any homeomorphism is in particular, it's a bijection from X to X. So homeo of X is sort of really like just the automorphisms X as a topological space. And in a topological space, it's just a set with some extra structure. And so the automorphisms preserving that extra structure certainly live in all automorphisms and sort of act on X. How you can arrange that. What else? Yeah, good. So that's sort of combining. So that's combining sort of this left multiplication action and the right multiplication action when you view it as a left action. So if you get So G acts on G by a G dot H is equal to GH G inverse. This is the conjugation action. Great. What else? Yeah, good. So if you have a complete vector field, so a complete vector field, well, I don't know differential topology terminology so well, but I guess complete means that you can sort of integrate the action completely fully on a manifold X. You get sort of an R action. So an example sort of would be like if you have a Lie group sort of, and you sort of exponentiate sort of some tangent vector, that would give you sort of a translation action. Okay, great. So, and for those who aren't familiar with this setup, and if you have a manifold, then sort of you can just sort of have, and then a vector field is just sort of a direction at each point, and then you sort of just like this action is sort of flow along the vector field. And so being complete just means sort of when you sort of write down this differential equation, that your solutions sort of exist to infinity. And so when they exist to infinity, like then that flow is really sort of an action of the real number, like of the additive group. Sort of where the additive groups sort of correspond to the time of your flow. Great. So in fact, I mean, this gives you a map. And we have another way to think about this is sort of we have diffeomorphisms of X acting on X, and this gives you a map. So integrating phi gives you a map from the real numbers to diffeomorphisms of X that are sort of adding on X. That's another way to think about this. Good. I mean, let me sort of bootstrap off of that to give another example that I sort of said out loud before, but sort of diffeos of X. So if X is a smooth manifold, then the diffeomorphisms, those are just sort of bijections that respect the smooth structure. So they're just smooth bijections. Well, that's not quite true. They're smooth bijections whose inverse is also smooth. Sorry about that. But so these are, and these act on X, but so they also act on sort of C infinity of X values. So these are sort of smooth R-valued functions on X. Just by sort of, if you have a diffeomorphism phi, then sort of you have some function, then phi dot f is equal to f of phi inverse of X. So this is this thing I was saying before, where sort of, well, if I wrote just f of phi of X, that would be a right action, not a left action, because sort of doing functions, so taking functions sort of reverses the, if you sit, and you have to do this once in your life, but you do it once in your life, you'll know that sort of taking functions sort of reverses the left and rightness of the action. So you sort of then put in an inverse to sort of get a left action still. But it's one way to think about how this is going on. I mean, there are sort of more natural ways to think about it maybe than sort of just satisfying abstract formalism. But okay, anyway, so this is also called pullback by phi, pullback of f by phi. So depending on by phi inverse, maybe. Okay, maybe not. This is so sort of another way to say it is sort of pull back by sort of functions, sort of reverses the order of composition. Good. So someone, great. I like this example. Someone just wrote that the symmetric group acts on K of x1 through xn, so on a polynomial ring. So a polynomial ring is a particular set just by sigma of f of x1 through xn is equal to sort of f of x sigma 1 x sigma n. Okay, good. So another way you can think about this is, e.g., if k is equal to the complex numbers, or let's say just real numbers, well, then then sigma acts on r to the, so Sn acts on r to n just by permuting coordinates. And then sort of what we just wrote down is sort of, this gives an action on smooth functions. Sort of by the last example. But in fact, sort of it also gives an action on polynomial functions inside of smooth functions. And sort of the above is the restriction to polynomial functions. I think it'll work out. But maybe. Probably this needs to be an inverse. Is that where you want the inverse? Yeah, I think that does need to be an inverse, but I can't. This is one of those ones where at least one of us will have to sit down and sort of work it out in there. I work it out carefully to make sure, but I think you're right. There should be an inverse there. By sort of don't quote me on that. I've purposely written it sort of vague enough that someone looking at the notes won't be able to tell. You're right. Yeah. Well, okay. Let's. One can sort this out, but I know I'll make a mistake sorting it out, trying to sort it out loud. So let me not. Thank you. Okay, so good. Okay, so that's a lot of actions. I mean, in particular, I wanted to sort of get to this point that we sort of saw a little bit. So let's actually trace a theme through. So first, we sort of had Sn acting on the set 1 through n. Then you can sort of upgrade that to an action of Sn on r to the n just by sort of replacing, like, so you can take that set 1 through n, and then you can sort of just take like the free vector space on those symbols. So you can sort of treat 1 through n as sort of being the basis vectors for r to n. And so then that action on the set of basis vectors sort of upgrades to an action sort of on r to the n, just sort of by extending it by linearity. And then that's action on r to the n now sort of upgraded to like an action on smooth functions or polynomial functions. So this is an important thing about group actions that sort of won't matter so much right away, but will matter much more later on, like when we talk about representation theory, and sort of, when especially sort of in anything you do in life with group actions beyond this class, is that sort of when you start with one group action, like you can always build new group actions out of it. And sort of, it's often like, instead of having a group acting on a set, like it's maybe nicer to have a group acting on a vector space or a sort of a polynomial ring. Like sort of, if the thing you're acting on has more structure, you can then use that structure to study the group action. And that turns out to be really fruitful. So we'll see something about that when we get to representation theory, like how you can get more information when you sort of pass from sort of, like, for example, this permutation action on sort of the basis vectors to this linear action on Rn. Like this actually sort of lets you do things you couldn't do before. Okay, great. So, but that's good. So these are lots of group actions, and these are all good examples to keep in mind. So on this theme, let me sort of do another example on the theme of sort of producing new group actions from old. So we have this group D8, which is contained in the orthogonal group. So O2 is sort of rigid transformations so rigid linear transformations of R2. So there's just the linear transformations that sort of respect distance, or equivalently the ones that preserve the inner product, the standard inner product. Okay, and then so we have the dihedral group inside of there is equal to the subgroup preserving the square. That's how we defined it. So we define it as the rigid symmetries of the square. So really the square about the origin. So I mean the square. Let me draw this. The square centered at the origin. And so, and I stated but never proved, and that's fine. I'll never prove it, but you can look up a proof somewhere. That this has 8 elements. So there are 4 rotations and 4 reflections. So the reflections about sort of the bisectors and the diagonals preserve this, and the rotations preserve it. Okay, so, but once I have a rigid transformation, if I have a rigid transformation that preserves the square, then it also preserves sort of other things. So for example, it preserves sort of D8 acts on sort of, well, all points of the square. So I can literally think of sort of this dihedral group as sort of acting on just the set of points in that square, which is some infinite set. But it also just acts on all the vertices of the square. So the 4 vertices of the square. Because I mean, this action on all the points in particular, it sends like one vertex to another vertex. So by vertex, I mean corner. So it sends sort of one corner to another corner. It acts on sort of the 4 sides of the square. And it acts on sort of the two diagonals of the square. So this is a 4-element set, 4-element set, and 2-element set. Sort of sends a diagonal to the other diagonal. So, okay. I mean, it also acts on sort of anything you can construct, sort of using sort of like nice sort of rigid constructions out of this. So it also acts on sort of the following. I can take my square, then let me sort of bisect each pair of sides, and let me also sort of draw in the diagonals. So it acts on this shape. Essentially because since D8 sort of preserves since D8 sort of, well, it preserves like opposite sides, like it also preserves sort of the line bisecting between the opposite sides, because sort of it also preserves distances. You can think about this sort of ways, and so we sort of repeat this, and the point is sort of this idea that you can sort of build actions from other actions, like sort of works geometrically too. Okay, so we'll come back to that in a second. Let me highlight this picture because we're going to use it in a moment. If I highlight it, I'll be able to find it. Okay, so what are the kinds of things we study about group actions? So, and the big thing is orbits. So if G acts on X, we say sort of an orbit is an equivalence class for the relation so an orbit of the action of G on X is the equivalence class for the relation sort of X1 is similar to X2 if and only if there exists an element of your group G, little g, such that Gx1 is equal to Gx2 is equal to X2. So okay, that's a fancy way to say sort of an orbit is an orbit. I mean, it's just the set of elements you can sort of reach, where you can sort of always reach one from the other using the action of G. So it's elementary to verify that this is an equivalence relation. Okay, so let's go back to our example. So what are the orbits for sort of D8 acting on the vertices of this picture? So a vertex, I'll just draw a dot, everything I mean by vertex. So vertex is just sort of a place where two lines intersect. Right, so what are the orbits for D8 acting on these vertices? Okay, so it's a question, so there's a question mark. Why don't we all take just a couple of minutes to think about this, and then we'll discuss in group. In fact, let me sort of upgrade it. You can also do the edges. So an edge is now just a line between two vertices. And this is supposed to be a square, even though it looks like a rectangle. Yeah, good. So yeah, I think probably it's been enough time. So people can just start throwing out some orbits. So that's one orbit. So let me draw that orbit in red. So that central vertex is just 0. And so any linear transformation sends 0 to 0. So definitely, sort of since D8 sort of lives inside of linear transformations, that's just sent to itself. What are some, so what's the orbit of one of these, like this top left corner? Yeah, so all the corners. So we already said sort of out loud, at least, that like it could, like sort of the action D8 sort of preserve the corners of the square. And so it just remains to check that you can get from any one corner to another, but like using the, so how can you get from like this corner to this corner? Sorry, this corner was the top left. How can you get from the top left corner to the bottom right corner using a group action, a group element? So yeah, so Antonio said by reflection, so reflection along this diagonal. Can someone give me another way? Yeah, you could also rotate 180 degrees. That would also take the corner of the door. So there's actually 2 different ways to get there, but that's fine. It doesn't matter how many different ways there are to get from one to the other. It's still same orbit. Okay, and Good. And so similarly, we see that these other vertices sort of on the middle are also in the same orbit. So again, sort of the reflections. Well, yeah, okay, good. So you can just, again, use the rotations to get from any one to another. Okay, good. So how about the edges? So what if I take, like this edge right here, this sort of top left diagonal edge? Yeah, good. So that one, it's just like the vertices that all go all diagonals. I mean, you can either just sort of say, like, do the same work to see this, or I might run out of colors. This will be orange though. Or you could just say, like, well, if I sort of take this edge, like, well, it has to become an edge from a blue dot to a red dot. And so there's only one red dot, so that doesn't change. And sort of, and I know I can get from any one blue dot to any other blue dot. So I sort of, whoops, that's not my one. So I can get to all of them. Okay, and similarly, if I look at these edges from the red dot to the green dot, the same logic applies, and you see those live in one orbit. Good, and so then there's, what's the orbit of this edge right here? Yeah, it's the remaining edges. Good, so I don't have to color it in, but maybe I'll just thicken, well, maybe I will anyway, just for. So to get from this edge to this edge, what do I do? Sorry, you can't see what I just said. From this edge to this edge, what do I do? Yeah, I just reflect about this axis. And then now, once I have these two, I can just sort of rotate to get the rest. Okay, good. So let's see, how did I set this up? Pretty well. Let's see. It'd be nicer if I had one more thing in here. Well, okay, anyway, it doesn't matter. This is a good picture. Right, so, okay, so this is sort of an idea of sort of what orbits look like and sort of how you can compute them. But this is just idea. If you want to, like, if you have a group action, you want to compute orbits. Like, what you do is you sort of just, okay, you say, I'm going to start with a point and see sort of everywhere I can get to from that point by using the group action. So you can think about the orbit generated by a point. So any point is in a unique equivalence class, and sort of, if you look at the definition of the equivalence class, like exactly what it means is sort of, it's just all, like, an orbit is just sort of all the points you can get to when you start at some fixed point. But sort of you can start at any point in the orbit, it doesn't matter where. So there's some redundancy about where you start, because you can start at any point in the orbit and then look at where you sort of get. So if you want to sort of compute all the orbits of some group action on something, you just sort of pick one thing. So like we picked this top left corner and we said, where does this go? And sort of then we colored in that equivalence class, and then we sort of said, okay, now, like, what's the next thing that we haven't colored yet? Let's look at where that goes. And this green one, and so on. So this is sort of how you can break down orbits. And I mean, this illustrates also sort of an important principle, which is sort of, if G acts on X, then X can just be written as the disjoint union over all O and orbits of X, or O, the orbits of G acting on X of O. So this is sort of like a curly scripto, maybe a German. I don't know how, maybe I would, if I were typesetting this, I would probably typeset an orbit as maybe using mathfrak of a lowercase o would be a good way to typeset an orbit. So you might sort of look on the internet and see whether anyone else agrees with that. But this is true for any equivalence relation, right? I mean, anytime you have an equivalence relation on a set, well, that set is sort of partitioned into the equivalence classes. So here, I mean, orbits are just, and this is just a specific type of equivalence relation. And so your set is partitioned into these. So, so here's the main result of group actions. And this is sort of, this basically innocent fact is what like all of the like main applications of group actions, especially to sort of finite groups, are based on. So if X is a finite set, then, and Gx on X, then the size of X is just the sum over all the orbits of the size of the orbit. So this is true whenever you sort of partition a set into subsets. The size of the set is sort of equal to the sum of the size of the subsets in your partition. So here I'm using this is really a disjoint union into the orbits. Okay, so let's give a corollary of this. So let me give an example for how you apply this thing. Let me think. Actually, let's take a 5-minute break. Probably now's a good time, and then sort of we'll give just a simple application of this idea. So we'll resume at 1:15-ish. Maybe let's say 1:16. Okay, so let's do theorem. It's called Lagrange's theorem. And if you don't remember the name, you probably remember the statement, which is G is a finite group. And H is a subgroup of G, then the order of H, so the number of elements in H, divides the number of elements in G. So, sorry, this doesn't look clear, but this says the size of H divides the size of G. Okay, so what's the proof? Well, let's look at the action of H via left multiplication. So H, the subgroup, acts on G via left multiplication. Okay, and so G is the disjoint union of the orbits. So the size of G is equal to the sum over all the orbits of the size of O. But what's the size of an orbit? Well, if X is contained, so let me say, so if G is contained in some orbit, then sort of O is just sort of the set of all the elements I can get to sort of by multiplying G by itself. So it's just the subset of G of all the elements I can get to sort of by multiplying by an element of H. But sort of these are all distinct. So for H1 not equal to H2, H1G is not equal to H2 of G. So I mean, this is just by like the cancellation property for group multiplication. Like if you know if sort of H1 times G is equal to H2 times G, then H1 is equal to H2. But so that means these are all distinct for sort of these elements HG are all distinct as I vary over the elements of H. So the size of this orbit is just the size of H. So that means the size of G is equal to the number of orbits. And then all the orbits are the same size, so they're all size H, which exactly says that the size of H divides the size of G. Okay, good. So that's Lagrange's theorem. And it introduces sort of this important space. So let me make a definition. So we can so by thinking about a little bit more about what was going on in this proof, we can sort of say a little bit more. So let me make a definition. So the left so the right cosets of H and G are the orbits of H acting on G via left multiplication. So this looks a little silly, why these are called right cosets when it's the orbits for left multiplication. We'll come back to that in a second. But so we call these, we just write them as sort of H mod G. So this sort of notation sort of, it sort of suggests the fact that sort of two elements in G are sort of in the same orbit if they sort of differ by multiplication by H on the left. So the left cosets of G and H, let's start H and G, are the orbits of H acting via right multiplication on G. And so if we write these as G mod H on the right. Okay. So the reason sort of for the notation is because G acts from the left on G mod H, and G acts from the right on H mod G. So this is sort of interesting. So we start by looking at the left action of H on G via left multiplication. So this is by right multiplication. And here, this is by left multiplication. So and somehow the point of this is that like multiplying on the left and multiplying on the right, like they don't interact with each other at all. Like it doesn't matter what order you do, like if you multiply on the left and then multiply on the right, like it doesn't matter what order you do that in. So this like multiplication on the left sends one orbit for multiplication on the right to a different orbit. That's why sort of you get these group actions. And this is literally the statement sort of that G acts on the set of orbits for right multiplication by H. Like that's sort of what this is saying. Okay, and so sort of the right coset or left coset, like the right or left here is referring to the action of G on this. So this is a left action, like G acts on the left on left cosets and it acts on the right on right cosets. Or sort of acts by left multiplication on left cosets and by right multiplication on right cosets. Okay, so good. These are really important. So make another definition. So a G set, sorry. We say G acts on X transitively if there's a single orbit. Okay, so we state theorem. This is the classification theorem for G sets. Okay, so a G set is just, it's a set with a left G action. And you can sort of get, and you get another classification theorem for right G sets that looks the exact same, just sort of you put right everywhere. So 1, any transitive G set is isomorphic to G mod H for some H. And 2, any G set X has a unique decomposition X is equal to the disjoint union I and I, Xi for sort of Xi contained in X subsets on which G acts transitively. So their subsets are preserved by the G action. On which that sort of action is transitive. So the action being transitive just means you can get from any element to any other element in that set by sort of by acting by some element G. Okay, so what's the proof of 2? And what's another name for these sets Xi that I wrote down? Yeah, exactly. So, I mean, somehow the theory of like group actions was a theory that was developed before. I mean, it's like and it's just one of these examples where there's like a theory that like is the exact same as every other theory, but sort of it was so important and developed so early on, and like it has sort of its own language for everything. So, like the orbits of a G action like are just sort of the simple subobjects. So like this is a category that has simple subobjects in it. Like G sets is sort of a semi-simple category. So a semi-simple category is sort of as a category where there are sort of these irreducible blocks and everything is just sort of given by a direct sum of those irreducible blocks. So it's like sort of the categorical version of the prime numbers. Prime numbers are a simple category because like sort of the categorical version of like sort of factorization, like sort of any integer sort of factors uniquely into prime numbers. Any G set sort of decomposes uniquely into sort of simple G sets. These simple G sets and then are all of some specific form is the second part of this. But this first part is just saying, yeah. So and a better name besides transitive group action would be simple G set. And that's sort of a name like simple G set sort of is sort of the analog in this category of G sets of sort of what it means to be a simple group or what it means to be like a simple module. So like a transitive G set is sort of just a simple G set. Okay, and sort of the orbits in an arbitrary G set are sort of just the decomposition of an arbitrary G set into its simple subobjects. So this is sort of just some philosophy. So 1, this is something you've all probably seen before, but let me just sort of state it as an exercise. And just an exercise to sort of like go through the proof carefully, but let me just say how it works. If G acts on X transitively, then sort of fix sort of some point little x in x. And then we're going to write sort of stabilizer of x is going to be a subgroup of G. And this is just equal to the set of all G and G such that G times X is equal to X. So you can check that the stabilizer of any element and not just in any action is is a subgroup of G. So the stabilizer of an element is a subgroup of G. Then the map G mod H goes to X, so G mod the stabilizer of X, sending some element. And really by some element, I mean sort of, it sends, like if you have an orbit, just pick some element in that orbit. So you send G to G times little x. So this is well-defined. So that means, well-defined means sort of, this didn't depend on which element of the orbit I took, so which element of the coset I took, and an isomorphism of G sets. So it's not just that it's a bijection, but really, I mean, there's a natural action, like this is a G set. There's an action on the left of like G acts by a left multiplication on this orbit space, sorry, on this set of cosets. And this map respects that left multiplication action. Right? That's sort of obvious from the formula once you know the formula is defined. So you just have to check that this is a bijection and that sort of respects the G action. Okay. Let's go back to our example from above. Whoops, very big. Okay, so so what do I want to look at? So, well, we had sort of D8 acting on the square. And in particular, it acted sort of on the like we saw the vertex, the corners of the square. So the corners of the square are a simple G set. So a simple D8 set, that just again means D8 acts transitively. Okay, so let me name some of these. Just name all the corners, P, Q, and R, P, Q, R, and S. So and we already sort of worked out in our example that this was an orbit. So this is sort of really a transitive action on this set. So what is the stabilizer of P? Which reflection? Yeah, good. So let me sort of draw that. So let me call this L. Actually, then we call it PS, the line segment from P to S. So the stabilizer, well, one element of the stabilizer is reflection about this line from P to S. What's another element of the stabilizer? The identity, right? So it's a subgroup, so it always contains the identity element, but also the identity element always fixes everything by its definition of a group axiom. Okay, and so this is a subgroup because if you take this reflection, you square it, you just get the identity. So you reflect twice, you get back to where you started. Okay, and so so we get sort of an isomorphism of sort of D8 sets from D8 mod stabilizer of P to sort of the corners of the square that just sends sort of an element of this set over here to sort of G goes to G of P. So G dot P. Okay, so this is one. What's the stabilizer of Q? So Q is this top right vertex. Yeah, good. So this line RQ. And so we get D8 mod the stabilizer of Q, also isomorphic to the corners of the square. By G maps to G dot Q. Okay. Me do one more, but I won't make you sort of spell it out for me. But so what's the stabilizer of R? Well, the stabilizer of R, well, it's equal to stabilizer of P. Sorry, it's equal to stabilizer of Q. And the stabilizer of R is sort of the same reflection. And so you get an isomorphism. And sort of the same subgroup, so the same quotient to corners of the square. Sending G to G dot R. Okay, so someone tell me the point I'm trying to make. They all have two elements. All the stabilizers have two elements, that's true. But it's more than that. The point is they all have, like, these stabilizers have two elements, but like everything I wrote down here is different. So on the right-hand side, I always have corners of the square. The corners of the square is sort of makes 100%, it's 100% unambiguous what that means. The corners of the square is a set with an action D8. Over here, well, I have two different sort of coset spaces. I have sort of D8 mod stabilizer of P, and they have D8 mod stabilizer of Q, which is the same as sort of D8 mod stabilizer of R. So stabilizer of R is equal to stabilizer of Q. So like these two things are, these two coset spaces are the same because the subgroup is the same. But these two maps are different. like the map from D8 mod the stabilizer of Q that I wrote down, like this map I wrote down sends the identity to Q. And this map I wrote down sends the identity to R. So the point is there's sort of nothing unique about, sort of this way you can express an arbitrary sort of simple G set or arbitrary transitive G set as G mod H. So there's not necessarily a single subgroup. So H might be different. Like there's sort of here we had two different H that I could use. And then also, even if you sort of fix the same, like even for a single H, there are different choices of isomorphism. So you can sort of take the orbit map sort of starting at any point. So really, I mean, this happened in the proof already. Like if in the proof to get an isomorphism, so we fixed a point, and sort of then we got a sort of isomorphism from sort of G mod the stabilizer at that point. But really, like if you fix a different point, you get a different isomorphism, and like you might also like sort of depending on your setup, it's possible that even the subgroup that's showing up on the left, like the stabilizer subgroup, doesn't have to be the same. Does someone see what the relation between these two different subgroups is that showed up? Yeah, they're conjugate, exactly. So let me sort of state everything. Observation. In sort of 1, the identification sort of G mod H isomorphic to X sort of really is not canonical. So what's canonical is if you sort of fix a point. Then sort of you get sort of a natural isomorphism from G mod the stabilizer of X to isomorphic to X. But sort of different choices lead to different isomorphisms. And possibly different subgroups. So this is sort of an important just thing to have in your head. The stabilizer of any 2 points in a G set, in like a transitive G set. So if you have a G set that's not transitive, then there's no reason to expect any relation between the stabilizer of 2 points. But in a transitive G set, even then, like the stabilizer of 2 points is not necessarily the same. All you know is that they're conjugate. And so in fact, you can prove that. So fact/exercise. So if G acts on X and X in X is some element in X, then the stabilizer of G times X is equal to the conjugate of the stabilizer X by G. Corollary is sort of if G acts on X transitively, then the stabilizers, not only are they all conjugate, they actually form a conjugacy class of subgroups. And another way you can sort of write this down is sort of, okay, so this is just, well, this is a fun way to think about how you can use the structure. So if X is a G set, then there's a natural map from the G set X to the set of subgroups of G, sending X to stabilizer of X. So G acts on this by conjugation on the set of subgroups. So if you conjugate a subgroup by an element of G, you get a new subgroup. And so a way to summarize this fact / exercise and corollary are just the statement that this, like the map that sends a point in a G set to the stabilizer is actually a map of G sets, the map from the G set X to the G set of subgroups of G, the set of subgroups of G, where the G set G action is by conjugation. And so orbits over here are exactly conjugacy classes of subgroups. And so, I mean, if you have an orbit over here, it gets mapped to an orbit over here. Sort of a nice way you can sort of encode this theory in your head. Okay, so yeah, I guess we better stop there because it's 1:45. So we'll pick up. So we'll pick up with some some consequences for finite group theory. So some more consequences for actions of finite groups next time. So I'm going to stop the video, but I'll stick around for a few minutes if anyone has questions.